Okay, so moving on, what I want to do now is an example. But we have many examples, and this example is an important example. It's not just an example, it's an example that we're going to use a lot. So the example is the following. I want to show that this function, sine x over x, has a limit as x approaches 0. Note that it's not defined at 0, right? But as x approaches 0, it has a limit, and that limit is 1. And I want to prove this. And none of the tools that we developed so far can handle this. Okay, so all the limit arithmetics won't work because the bottom goes to 0, so we can't do quotient, right? Do you agree? Bounded times something that goes to 0. Well, that's not the situation here. You can write it as sine x times 1 over x, but then 1 over x is not bounded, right? So that's not going to work either. You can try sandwiching it. Well, we're going to use sandwich somewhere in the proof, but there are more arguments needed here. So we're going to work a bit to do this, and then we're going to use it a lot. Okay? So, remarks before we show this. Remarks. One, very important example, in the sense that it's very useful. Remark 2, note that limit arithmetics fail. We can't use quotient. And the third remark, I want to quickly draw this function to see what it looks like. We did it already, but let's do it with a bit more detail. So it has this sine wave-ishness in it, right? It's sine x. Do you agree? And I'm multiplying it by 1 over x. 1 over x looks like this, right? Does everybody agree? So it gets smaller and smaller as we head out towards infinity. Do you agree? So this thing is going to look something like a sine wave that gets multiplied by things that are smaller and smaller as we head out. Do you agree? Then its behavior as we head out should be something like this. Oh, let's make it in blue. Its behavior as we head out towards infinity and towards negative infinity is going to be something like this. It gets, and likewise here, it's like a sine wave, but one that gets that the amplitude becomes smaller and smaller as you head out. And then this statement that we're going to prove is going to show that as you go towards 0, it's going to have a limit, and that limit is 1. I'm going to draw an excessively big hole here just to indicate that at 0 itself it's not defined. Okay? So this is what the function looks like. Okay? Okay, so let's prove this statement. And the statement is going to start back in ancient Greece, in geometry. Okay, maybe even ancient Egypt, I don't know, or ancient China. Geometry goes a long way back. So I want to draw a unit circle, or at least part of it. So this is the unit circle in orange, meaning that where it intercepts the axes is exactly at 1. Okay, so it's a circle of radius 1. Good? Say yes. Thank you. And now I'm going to take some angle here. So let's make it maybe, is it important? Not really. Let's make some angle here and call it, I want to call the angle x. Okay, so no, this axis is not the x-axis, it's the, what's the first letter of your name? No, N. This is the n-axis. Okay, because I want to call the angle x. Okay, so do you agree that if I look at the point here, at this point here, and if I take project down to the x-axis, the n-axis, I get a right triangle, and this, the hypotenuse is 1, because it's the radius of this unit circle, right? What is the length of this thing? This is precisely sine of x. Does everybody agree to that? Because sine of x is this divided by this, right? Basic trig. Sine of x is this divided by this. This is 1, so this is just sine of x, right? Now this arc, this orange arc here, if x is given in radians, what is the length of this arc? Do you know? Right. This is x. This orange arc from here to here is precisely x. Okay? Some people look at me as if this is, I just said something very mysterious. Well, remember what radians are. Radians are dividing the circle into 2 pi pieces, right? So this angle, what portion does it cut from the entire circle? Think of this as a slice of a cake. Better yet, a slice of a pie. What portion is this slice of the pie? It's x out of 2 pi. Do you agree? What's the circumference of this circle? 2 pi r, but what is r? 1. So the circumference of the pi is 2 pi. Do you agree? So what is this out of the circumference? It's the same as the ratio between this and the 2 pi radians, so this is x. Sorry, this was x out of 2 pi, so this has to be the same ratio, so this is x. Do you agree? Everybody convinced? So what we learned from this is that, at least for x's, which are greater than 0 and less than pi over 2, which are honest angles in a triangle, we have that sine of x is less than x. Because this line is clearly shorter than going to a further point and not even taking the direct route to it. Does everybody agree? Yes? Okay. Now what I want to do is take this point here and see which point projects down to it from this line. So it's going to be about somewhere here. And once again, I get a right triangle here, except it's a bigger right triangle. Do you see it? The bigger right triangle. Do you see it? And what is the length of this line now? This new black. Y1. Easier. Look, now this is 1. Look here. This is 1. Tangents of x is this divided by this. Do you agree? So tangents of x is this divided by 1. So this is just tan x. Do you agree to that? So what I want to claim now is that this is longer than this orange x orange line here. So I want to claim that this is less than tan x. It's kind of convincing from the picture, but a bit less than the fact that x is greater than sine x. Because maybe, if we straighten this out, it will exactly do this. So why is that not the case? So one way to think of it is, so it's clear that this slice of the pie is smaller in area than this bigger triangle, right? It's clear that the size of this slice is less than the size of this bigger right triangle. Does everybody agree to that? Yes? Because it sits inside. What's the size of this triangle? Well, the size of a triangle is the base times the height divided by 2, right? The base is 1, the height is 10, divided by 2. So the size of the big triangle is 10x over 2. Do you agree? What's the area of the slice? What's the area of the slice of the pie? Well, the area of the entire circle is what? The area of the entire pie is pi times the radius squared. So it's pi times 1 squared, so it's pi, right? And the slice is x over 2 pi of that area, right? So the slice of this thing is x over 2 pi times pi. Do you agree? Which makes it x over 2. So x over 2 is less than 10x over 2, so x is less than 10x. Does everybody agree? So all this geometry or trigonometry or however you want to think about it was to argue this fact. And this I'm going to use, and this I think we even mentioned previously, this fact, when we calculated the limit of sine x. Remember we had a certain statement like that sine x is less than x? And I told you I'll prove it later. Remember that?
Without the tan.
Without the tan. Just this thing we had before. We had it in absolute values, in fact. Okay? And so this is what I wanted. This is why all this showed up. And so this is for x's in this region. But let's now draw the graphs of sine x and sine x and tan x and x. So we know now that here's x. This is x. This is the function y equals x. We know now that sine of x has to live underneath until pi over 2. That's what we proved. So we know that the picture is something like this. But clearly, once we pass pi over 2, sine starts going down, right? So clearly this fact that sine of x is less than x extends now not just to x's between 0 and pi over 2, but to all positive x's. Does everybody agree to that? Moreover, sine is an odd function. X is an odd function as well. So if x was greater than sine of x, for positive numbers, we're going to have a mirror image here. It's going to be, sine x is going to be greater than x for negative numbers. Do you agree? Everybody? And similarly, the argument for tan x, which is also an odd function. So tan x, now we know we need to draw above the x, and it's going to go below once we're here. Clear? For the other branches, different things are going to happen. But the point is that what we see now is that, first of all, we can say that sine of x is less than x in absolute value, and this is true for any x, or if we add less than or equal, now it's true for any x. And that's what we used, and we're going to use that fact more and more. Okay? And in addition, we can extend the inequality sin x less than tan x. We can extend it to negative numbers, but the direction of the inequality would change. Okay? Question?
For example, I'm thinking about tan x is always bigger than x. Pi over 2 is bigger than 1, but tan pi over 2 is 1.
Tan x is bigger than x. So what are you saying? Tan of pi over 2 is not defined. Tan has an asymptote here, right? You know what tangents looks like. So tan of pi over 2 is not defined. Tangents has an asymptote here. Right?
So always tan x is bigger than x.
Not always, because there's going to be a new branch here, right?
Between 0 and pi over 2.
Between pi over 2 and 3 pi over 2. Between 0 and pi over 2, no, between 0 and pi over 2, tan is bigger than x. Between minus pi over 2 and 0, tan is smaller than x. Okay, the roles interchange when we look at the negative ones. Okay, that's what we drew. Okay, so now, using all these facts, I want to go back to what we wanted to prove. We wanted to prove that sine x over x approaches 1 as x approaches 0. So now we have all these facts, so let's do it. So for x is greater than 0, we know, or x is greater than 0 less than pi over 2, we know that sine x is less than x is less than tan x. We can take this inequality, everything is positive here, so we can, sine x is greater than 0 in this region, so we can do reciprocals to the entire thing. Do you agree? And the direction of the inequalities will remain, when we do reciprocals, the directions of the inequality change, right? So we get, in this region, 1 over sine x is greater than 1 over x, is greater than 1 over tan x. Does everybody agree?
How you did that?
I did reciprocals. I did 1 over. When a is less than b, 1 over a is greater than 1 over b.
The mirror on the x, right? Okay.
Now, I'm going to multiply everything by sine x. Sine x is positive, so the inequalities don't change now. So I get 1 is greater than sine x over x, which in turn is greater than sine x over tangents of x.
1 over cosine.
Tangents of x is sine over cosine.
No.
1 over tangents of x is cosine over sine. Multiplied by sine, we just get cosine here. Did everybody follow this step?
Right.
Replace tan with sine over cosine. Good? Cosine over sine, multiply by sine, like I did to the entire equality, I just get cosine. Now sandwich it. As x goes to 0 plus, what does this go to? 1. As x goes to 0 plus, what does 1 go to? 1. Sandwich, as x goes to 0 plus, this goes to 1. Do you agree? And in order to wrap up this proof, you need to argue the same thing for x's between 0 and minus pi over 2 and do the left-sided limit, but it's the same argument precisely. Okay, so similarly for the limit x goes to 0 minus, because all this statement was only valid for x's in this region. That's why I can only take the right-sided limits. Okay? All this statement only had a life for positive x's.
And you cannot include there the 0?
No, in 0 it's not defined. I'm doing reciprocals. Any of these are not defined at 0. Okay? So you do the similar thing for x goes to 0 minus, and then you use the theorem. If the right sided limit and the left-sided limit both exist and are equal, conclusion, sine x over x goes to 1 as x goes to 0. And this is the proof of this fact. And remember how hard we worked to do it. Okay, but we're going to use it a whole lot. Okay? Yes, question. Wait, there was a question here first.
I was wondering, do we need this graph for the proof?
Yeah, the point where we used this graph here was for the statement on the negative values. So we're using the fact that all these functions are odd to argue that this inequality, sine x is less than x is less than 10x, is the same on this side but in reverse order. Sine x is greater than x is greater than 10x. And then we have to do this argument, this entire argument, we have to run through when x goes to 0 minus. And that's going to be the situation where x's are between negative pi over 2 and 0. And only the two of them put together give me the limit as x approaches 0.
So the sandwich theorem still holds when the upper and lower...
The sandwich theorem still holds, the sandwich theorem still holds for one-sided limits. That's what we're using here. We're not applying the sandwich theorem on both at once. We're multiplying the sandwich theorem on the right, and this one is strictly bigger than this, is strictly bigger than this on the entire right neighborhood. And then we're separately applying the sandwich theorem from the left. Clear? Yes?
My question was, why can't we use this proof as a proof that 0 over 0 is 1?
That 0 what?
Over 0 is 1.
Because 0 over 0 is not 1. 0 over 0 is not defined. What we got here is that in a particular situation where you have a function going to 0 divided by a function going to 0, we got that the limit is 1. But I can give you an example of a situation where we have a function going to 0 divided by a function going to 0, and the limit is going to be, give me a number. I can give you an example where the limit is 3. Can you give me that example?
Yeah.
For example?
If you have like a polynomial which is consistent.
Easy.
3 sine x over x.
3 sine x divided by x. The limit is going to be 3. Do you agree? And it's still a situation of 0 over 0 in quotation marks. Okay? So 0 over 0, hence 0 over 0 is not defined. It's not a limit that when we see a 0 over 0 situation, we can automatically deduce what the limit is. Different examples, different limits. Okay? Okay. I want to mention very quickly one more theorem regarding one-sided limits. I'm not going to prove it, but we are going to use it. Proving this is more challenging. This theorem is not so. Let me say this: everything we did so far, if you're on top of things, if you're understanding what we're doing and you feel good and you're not intimidated by the epsilon delta definition, you can really do all the proofs that we did so far. You may need to think about them, you may need some hints here and there, but none of them are beyond your abilities. This theorem, for example, is harder. I'm not saying none of you can do it, but there's more hidden in the proof, and I can't explain that because I'm not showing you the proof. So I'm just going to quote it. Theorem. So assume f is monotone on some interval, I don't know, AB. So we're looking at a function that is monotone, either increasing or decreasing. Okay? And the claim is then f has one-sided limits at every point. Okay? So the kind of the hand-waving argument that may convince some of you is that if you think of a monotone function, going up, for example, okay? But it's not necessarily what we're going to call in a few lectures continuous. So it can have these jumps, for example. It can be monotone, 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 okay? So it's not necessarily continuous, okay? We're just doing intuition, just intuition. But if you approach a point from the left, along a monotone function, what's the limit going to be? What is the value that you're going to approach? What's the value? Try to think. What's the value that you're going to approach when you approach along a monotone function from the right, from the left? The answer is you're going to approach the supremum of the values of the function. Because you're going up, 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 up. That up, up, up is a set of y values, right? It's going to have a supremum. And that's going to be the limit when you approach from the left. When you approach from the right, if it's an increasing function, you're coming down along y values. That set of y values is going to have an infimum, and that's going to be your limit from the right. They don't necessarily have to be equal. It can be a situation like this. But they're both going to exist. That was very, very hand-waving and very vague, but that's the idea. Okay? How many people followed? Just the idea. Okay, good, good. If you didn't follow, don't panic. I can explain it again, maybe in the break. But we are going to use this fact. Okay, then monotone functions always have these one-sided limits, which are not necessarily equal. Okay, the next thing we want to discuss now is still the notion of a limit. But so on this board, I need to erase a board, but I just don't have the heart to erase this. So beautiful, isn't it? So maybe we'll move on to the next board and erase it. Also beautiful. Yeah, I know. Everything we write is beautiful. Pure art. But we need to erase something. So let me start the new topic. Okay. Later. Okay. Okay, so what I want to define now is the limit, but not when we approach a point A, but rather when we go to infinity. Can you imagine that? Going to infinity. So the picture you should have in mind is this is your L. And the function goes to, approaches that value L as we go to infinity. So here is maybe the graph, but as we head to infinity, f approaches that value L. Can you imagine that? Can you see what we're trying to say? Okay? And note that there's not an assumption that it approaches it necessarily from below or necessarily from above. It can cross the line. It can, in fact, cross it again and again and again, even when you go far out. But it gets closer and closer to this value L. Okay? How are we going to define it? Well, the y-axis portion of the definition is not going to change. we're going to want to say that whenever you take an epsilon, you get L plus epsilon and L minus epsilon. Instead of being close to the point, you want to say that when you're close to infinity, the values of the function live in this neighborhood of L. Okay, so you should maybe think of this infinitely long sleeve around the value L. So this orange, you should think of a long sleeve. And you should think of somehow being able to guarantee that if you go out far enough, the entire graph is going to live inside the sleeve. It's not going to go out. Let's maybe have it still go out here. Okay? So the way we're going to say it is the following. We say, so this is the definition. We say that the limit of f of x is L when x goes to infinity. This is different than what we had before. But still, L is finite. Okay, this is still a finite limit if for any epsilon there exists, what am I going to write here? How am I going to say there exists a delta neighborhood of infinity? What's a delta neighborhood of infinity? Any ideas? How do I say, right, the role of the delta was saying getting close to a point A. How do I say getting close to infinity? How do I say that? Okay, I can't use the word approaches infinity because that's what we're trying to define, right? We need to somehow say it in precise, very precise words without using the words approach or goes to or gets closer to themselves, right?
There exists a delta in the neighborhood of approaching infinity from the left.
Oh, you use the word approaching. Can't use the word approaching.
So just a neighborhood with infinity on the one hand side.
What's a neighborhood of infinity?
And on the left, like the right.
What's a right neighborhood of infinity?
Infinity.
Infinity minus delta, infinity plus delta?
No, infinity minus delta and infinity.
But what is infinity? It's not a number. Can you draw infinity on this axis?
So I can draw
Infinity is not a number. So in particular, there is no such neighborhood, infinity minus delta. Okay? So here's the way around it. The way to say we're getting bigger and bigger is saying just take an m. Go beyond it. You got closer to infinity. Now take a different m, go beyond that, you're even closer to infinity. Do you agree? That's what we're going to say. For any epsilon, there exists a value m such that if x exceeded m, that's it. If you went beyond m, that implies f of x minus L is less than epsilon. In the picture, similar to what we did before, suppose we want to be in this orange sleeve, in this orange epsilon neighborhood of L. So we go until we hit the graph. Once we hit the graph for the last time, then we go down. That's going to be our m. And any x greater than m, any x greater than m, any x greater than m is going to satisfy f of x is in that orange neighborhood. Do you see that? Any x greater than m is going to satisfy that f of x is in that orange neighborhood. What's the key word? What's the key word? Any. Very good. This is the key. This is the dynamics. The dynamics is because now we can take a smaller neighborhood, let's say this neighborhood in red, and this is now going to be the L plus epsilon, L minus epsilon. And if we want to guarantee being in this red skinnier sleeve, well, we're going to have to go beyond that original M, right? So the M corresponding to this will maybe be somewhere here. M. And now if you went beyond this M, any x beyond this M would satisfy that the values of f are in this red sleeve. Do you see that? And if you want to guarantee being inside this even tinier sleeve, you may need to go all the way, I'm moving to a separate board, all the way to that board or maybe beyond to guarantee that if you're bigger than that, you're in that sleeve. So that's the definition of the limit as x goes to infinity. Clear? Do you see that it's precisely the same idea as the definition of the limit at a point A, just modified to work for infinity? But it's still the idea, start on the y-axis, find how close you need to be to A or to infinity in order to guarantee that f of u is going to be in that epsilon neighborhood. Good? Okay. So the good news is, all the theorems, just like for, so let's write that maybe. Just like when we wrote down the definition of one-sided limits and then said, all the theorems hold. Just as in that case is going to be the situation here. So I'll write that. Remark. All theorems hold. What do I mean? I mean, for example, limit arithmetics. If you take a function that as x approaches infinity has a limit L, multiply it by a function that as x approaches infinity has a limit K, the product is going to be L times K. If you divide, the product is going to be L over K. If you want to take a function that approaches 0 as x goes to infinity, multiply it by a bounded function, the limit of the product is going to be 0. Okay? All the theorems that we had, all of them hold for limit infinity. Okay? So, for example, e.g., let's draw the sandwich theorem. What is the sandwich theorem going to look like? You, of course, have to modify the statements. You have to replace all the x approaches a's with x approaches infinity. Right? So what is the sandwich theorem going to look like? So picture corresponding to sandwich theorem. So we're going to have three functions. Here's our L. And we're going to have three functions. One, the bigger one we call G, I think, right? So this is going to be G. It's going to approach this L. Right? And then there's going to be, and approaching now is approaching at infinity. Do you see that? The smaller one is going to be maybe H. It's going to be less than or equal to G. But it's also going to approach L. So this is H. And the third one is going to be F, and that one's going to live in between G and H, right? F is less than or equal to G, greater than or equal to H. So it's somehow forced to live between the two, and it doesn't have much of a choice. As x goes to infinity, F, which is the orange one, doesn't have much of a choice. It's squeezed to approach L as well. Do you see that? Everybody? And stating the theorem is really just stating the exact same thing, just replacing x goes to a with x going to infinity. Okay? So that's the first remark. Second remark. So let's call this 1. Another remark. Similar definition for x goes to, right, for x goes to minus infinity. Minus infinity is over there. It's kind of far, okay? So you have to define it. Think how we would modify the definition of this definition. Think how you would modify this definition in order to say x goes to minus infinity. It's good practice. And again, so similar definition for x going to minus infinity, comma, all theorems hold. Okay? And everything is very intuitive here. I mean, for me, I even think that these limits as infinity even are even kind of more intuitive than limits at a point. Okay, because you kind of think of limits as something you go out to, right? Whereas limit at a point is something that's kind of artificial, right? Do you agree? Okay, the reason we present those first is that that's kind of the core of this entire subject of calculus, and these, well, we could have started off with these. Sometimes, by the way, we do start with these, but it doesn't really matter. Okay, so maybe one example. Do we have time to do an example? Barely. Okay, so let's just write it down, and you can fill in the details. So I'm going to give this as homework. Try it. The idea is really just to do the same thing that we did with epsilon delta, but now to do it with epsilon m. You get an epsilon. How do you find an m that guarantees f of x minus L is less than epsilon? Okay, so try to show.
You will solve it next lesson, right?
Hmm?
Are you going to solve this homework in the next lesson?
So the question is, am I going to do it on the board in the next lesson? Will you hold my hand? Will you help us? Try it. Maybe you'll come to me and say, hey, I tried it. Here, I got it. Is this correct? And I'm going to read and say, very good, you did it. And then I don't need to do it on the board, right? Don't be afraid of these things, okay? Try them. It's just like riding a bicycle. You may try it and suddenly panic. Hey, I don't know what to do. How do I continue? Then come and ask, and I'll give you a clue or a direction. Okay, but try it. Promise me that you'll try it. Don't wait for me to do it next time. Okay? Promise? Good. Try to show 1 over x, the limit, as x goes to infinity, of 1 over x is what? 0. Try to show this. Try to show using the definition. Okay? It's really easy for me. The first time you do things like this, they're really challenging. They're really hard. I remember that it was hard for me. Okay? So, but try it, please. Okay, let's finish up for today.